Okay, so question 2, here's our molecule. The first thing it wants is the name. So you know that some simple aromatic compounds are named just by calling them something benzene. But in this case that would be difficult because this thing would be hard to name as a branch. So what you're going to want to do is to call this side of the molecule the root of the name, and then the benzene ring will be the branch. So first thing is to identify the longest continuous chain. And you can see it goes 1, 2, 3, 4, 5, 6. So we've got a chain of 6, which is hex. It's got a double bond in it, which is ene. And we're going to start numbering this way round, because that way we keep the numbers as small as possible for that ending, which is what takes priority. So the ending of the name takes priority in the naming, and therefore we're going to number it that way around. So it's hex 2-ene. No EZ issue because we've got 2 methyl groups at this end, so there's no possibility of EZ isomers. And all that misses out is the extra methyl group here on carbon 2, and the benzene ring, which remember we call a phenyl group here. Okay, so that's a phenyl group at carbon 4. So it's 2 methyl for that group, and then 4 phenyl, hex 2-ene is the name. It then asks you how many pi electrons there would be in this molecule. Well, remember that when you form a pi system, there's always 1 electron in each of the participating p orbitals, which then overlap sideways to make the pi system. So in this case you've got a localized pi bond, so 2 p orbitals overlapping sideways, 1 electron each, so that will have 2 electrons in it. Here you've got 6 p orbitals participating, so another 6 electrons, and 6 plus 2 is equal to 8 pi electrons altogether. And then it asks us for an equation for incomplete combustion. So the first job there is that we're going to have to count the hydrogens, because regardless of how we draw the formula of the compound, we need to know how many hydrogens there are in order to balance the equation. So probably the easiest way to do that is just to go through and mark them on the diagram. So we can just go through and say, right, so there's 1 there, 2, 3, 4, 5. None there, because remember, if the ring's got a branch, you can't have anything else there, so it's 5 so far. But this carbon has only 3 bonds, so that's got 1 hydrogen, so that's 6, 7, 8, 9, 10, 11. Just making sure we've got 4 bonds for each carbon. So that's 11 so far, 12, 13, 14, 15, 16, 17, 18. So that suggests it's H18. We count the carbons, we've got 6, 7, 8, 9, 10, 11, 12, 13. So C13H18 is the molecular formula. The alternative way we could have done that would have been to say, right, well, if we got 13 carbons, if it was an alkane, remember for alkanes, we work with that CnH2n plus 2. So 13 doubled is 26 plus 2 is 28. And then the rule is that you lose 2 hydrogens for every ring. Okay, so that goes down to C13H26 due to the ring. And you lose 2 hydrogens for each double bond. So we'll lose 2 for that. And a benzene ring, remember, is equivalent to that. Although we don't usually draw it like that, you can do. And it therefore has 3 double bonds in it. So we'll lose 2 electrons for each of those, so that's 6 plus 2 for that one is 8, so we'll lose another 8 off there, which takes us to C13H18 due to the double bonds, and so we get the same answer. So you just have to decide which of those is more likely to get it correct for you. Then we can write our incomplete combustion equation. So we've got C13H18. There's no point really drawing the structure out. You can if you want. but because it's all going to be destroyed in a burning reaction, we can just use the molecular formula plus some O2s. And you have to remember that incomplete combustion means you don't get carbon dioxide, you get carbon monoxide, or possibly carbon, but carbon monoxide is what they're most likely to ask you for, so we'll put some CO in there, and the hydrogen ends up as water. You've got to remember what the products are. For complete combustion is CO2 and water, for incomplete combustion it's carbon monoxide and water. So 13 carbons means 13 COs, 18 hydrogens means 9 H2Os, because 9 2s are 18 hydrogens, and that just leaves that number to find. So we've got 13 oxygens there, plus another 9 makes 22. No oxygen so far on this side, so they're all in the form of O2. And so that wants to be 11 O2, and that's your equation. Part E is asking us to make our compound, this is compound X again, from benzene plus another organic molecule. So this is about the Friedel-Crafts reaction, which remember is a way of making a new carbon-carbon bond in order to attach some kind of side chain onto a benzene. And it's very easy to figure out what the other organic compound is, because all you have to do is copy out the molecule you're trying to make, which is that, and then where the benzene was going to go, you just say, right, what we need to start with is just to have a chlorine there instead. Okay, so wherever you want the benzene to be in your target molecule, you just say, right, what I want in the starting compound is just a chlorine in that same position. And if you react that with benzene, you need a halogen carrier catalyst. So AlCl3 or FeCl3 would do. Don't give alternatives, pick one or the other, but let's use AlCl3, and that will give us our product. And to balance that up, you need HCl, because we've lost the hydrogen from the ring and the chlorine from there, which make HCl. So that's the Friedel-Crafts reaction. So this is compound Y, and the aluminium chloride is the catalyst Z. Next it wants the mechanism for that Friedel-Crafts reaction. So remember, all of these aromatic reactions which you learn at A level are electrophilic substitutions. Electrophilic, remember, meaning that an electron pair is accepted by the thing that's attacking the ring, as we'll see in the mechanism in a minute. So electrophilic substitution is the name of the mechanism. And the first thing you have to do is demonstrate how the powerful electrophile is formed. So starting from the chlorocarbon, which was this compound, that first of all reacts with the catalyst. It's important that you draw the structure here. If you're still someone who prefers molecular formulae, you've got to grow out of that. Molecular formulae are really not much use in organic chemistry. It's all right in a burning equation or something like that where the structure doesn't matter. But any other time, if you just wrote C13H17Cl or whatever for that's missing the point, that it's the structure that matters, so please don't do that. So we've got that, and remember that what aluminium chloride always does is to grab Cl- from whatever it's reacting with. Okay, so it takes away that chlorine in the form of Cl-, and it'll leave a positive ion behind. So you'll get AlCl4-, and the important bit is that what it leaves behind, again, just copy it down. So it's not difficult, because you're just copying all the time, so you're not having to make up the structure. But the crucial thing is that where that chlorine was, there is now a positive charge. We've got a carbocation, and that's going to be our electrophile, because that's going to be very good at attracting an electron pair. So that's the next step. Here's our benzene ring. Here's our carbocation. Let's draw that again. Here's the carbocation, and that word electrophilic means an electron pair is accepted from the target, which is the benzene ring, to the electrophile, and it's got to go like this. Okay, so it's got to be very specific, that curly arrow. So it comes from the circle in the middle because it's a pair of electrons that's coming out from the delocalized pi system, and it's going specifically to that carbon. So you can't just have it vaguely pointing at this molecule. Don't point it at the positive charge either, because it's the atom that's accepting the pair of electrons. So that's what it should look like. And of course that's why if you just use molecular formulae you can't do that, because there is no specific carbon pointed then. So that will give you an intermediate which looks almost like your product, except that at the carbon where it's attached there's still a hydrogen there as well, and instead of the complete delocalized system you now have this. So the delocalized system goes around all 5 of the other carbons, but not the one that's formed the new bond, because obviously that's got 4 bonds of its own. It can't participate in the delocalized pi system anymore. And the positive charge has got to go somewhere, and where it goes is here, because it's spread around those 5 carbons. So that's your intermediate. It's screaming to get its intact delocalized system back again, so it wants to pull a pair of electrons back in, and it pulls them in from here. Okay, so from the bond, again, not from the hydrogen atom, not from that atom, but from the bond in between, because that's the shared pair, and it goes back into the ring to complete it. So that gives you your actual organic product. And the hydrogen that's been lost is lost in the form of H+, because it hasn't taken either of those 2 shared electrons with it, so it's an electron down. It's H+. We're nearly there now, but we're not quite there, because we've got to regenerate our catalyst. And, sorry, that should be AlCl4-, up there, because of course it grabbed Cl-, so we've got to turn that back into AlCl3. So we get AlCl4- plus H+. We'll regenerate our catalyst, so we get AlCl3 back, ready to go again and process the next molecule, and we get HCl, which is our other product, and that's the complete mechanism. So you have to make sure you can do those for this one, and for nitration, and for halogenation, but they're all very similar, so once you've understood what's going on, it's not difficult. Your final question then is, which of these words are appropriate to describe that molecule? That was compound X. So aromatic, any compound that contains a benzene ring is aromatic, so that one is clearly fine. Yeah, that's true. Now alicyclic means a compound that contains a ring which is not a benzene ring. So for example, if it had a cyclohexane ring, so you had something like that, that would be an alicyclic compound. Even if it has 1 or 2 alkene groups in it, it's still not a benzene ring, it's still not aromatic, so that would still be an alicyclic compound. But this one, its only ring is a benzene ring, so no, that one should be crossed out. Unsaturated means anything that contains a carbon-carbon double bond, and actually that would, I mean, that clearly applies here because you've got that, but that would also include a benzene ring, which is also, because of course it can be considered as having 3 carbon-carbon double bonds, so that's unsaturated as well. So yeah, that one is fine. Polar, remember the idea is that carbon and hydrogen have very similar electronegativities, so the bonds in this molecule are essentially non-polar. Unless it has oxygens or nitrogens or chlorines, something like that in it, you can consider it to be a non-polar molecule. So no, that one's not right. And the elixir of life, well, as far as I know, that hasn't been tested. It's just one of those experiments that's still on the list waiting to be done. So that's what, in the words of Donald Rumsfeld, you would call a known unknown. We don't know the answer to that, so you can cross it out or not. You have the freedom to make your choice there, and that's the end of the test.